Hi everyone, I'm Kumaro Kahadapitia, and in this presentation, I will introduce a pre-training strategy specifically designed for downstream activity detection, which only requires video level classification labels. This is a joint work with Zhao Ren, Haishang Li, Zhen Yu, Gan Hua, and Michael Ryu. The problem we tackle in this work arises when activity detection models are pre-trained for activity classification, which is usually the case due to data limitations. Such a pre-training is not ideal because there is a disparity between these two tasks, which I will discuss in the following slides. So as a solution, we design a new detection pre-training task on top of already existing classification data so that it is better aligned with the downstream. We do this without having to rely on any extra annotations. Before getting into the details, let's look at some prelims. What is activity detection and what is activity classification? Temporal activity detection focuses on making fine-grained predictions. In general, we need to predict one or more activity classes per frame. As the training pipeline for such a task requires per-frame annotations, which are expensive, detection datasets are generally small. For instance, Charade's dataset contains only 10,000 data points. Also, detection models need to preserve temporal information as they need to make fine-grained predictions. In contrast, activity classification focuses on video-level predictions. Classification clips are generally short, and since the annotations are relatively cheap, there are large-scale datasets. For instance, Kinetics 400 contains around 240,000 data points. And classification models can learn to aggregate temporal information as they need to make video level predictions. This does not complement detection models, which need to preserve temporal information in contrast, which means classification and detection are two different tasks. And having to train on one and later transferring to the other in the downstream is not ideal. In this work, we explore how detection pre-training can help the downstream. Previous works have pre-trained on classification and transferred to downstream detection due to data limitations. If we look at the characteristics of each sample dataset here, Kinetics 400 and Charades, pre-training data does only contain a single action per clip with video level annotations. However, the downstream data may contain multiple actions per frame, action segments, and frame level annotations. And with our strategy, we convert the same pre-training data, which is Kinetics 400, to have similar characteristics to the downstream data, which is Charades, so that we have a better aligned pre-training. We propose a weekly guided self-supervised detection pre-training strategy. Weekly guided in the sense that we use already available video level annotations. Self-supervised in the sense that we design a pre-text task which does not require any extra annotations. First, we extend video level labels to every frame, creating a pseudo frame level labels, which can be noisy. Then, we design a pre-text task based on what we call volume augmentations. They are intended to introduce one, action boundaries. As shown below, we call this augmentation volume freeze, which I will discuss shortly. And two, multi-action frames, as shown in volume mix-up and volume cut-mix augmentations below. Now let's look at each of these augmentations in more detail. Volume freeze introduces action boundaries to the pre-training data. This is motivated by the fact that detection models benefit from identifying action boundaries which arise from segmented actions. But the problem is that our pre-training data does contain only a single action per clip. So how can we introduce a notion of action segments to such data? What we propose is to create a motionless segment within a given clip and consider such frozen segments as background. By doing so, we create segmented actions and hence action boundaries. More specifically, we randomly select a frame and replicate it a random time interval, annotating it as a background class. Our assumption here is that without any motion, there cannot be any action. We understand that this is rather a strong assumption, which may not always hold, as some actions may be identified with only the appearance, even without any motion. However, our ablations show that these models trained with volume freeze have improved predictions around action boundaries. Even being noisy, the change in motion patterns has helped the model to identify action boundaries in the downstream. Next, let's look at volume mix-up, which introduces multi-action frames. Inspired by mix-up in the image domain, here we combine multiple clips with a seamlessly varying temporal alpha mask. Here we have an emphasis on seamless as it helps preserve temporal consistency in the resulting augmented clip. For instance, here we show a randomly selected set of clips of skiing and sailing. We merge these two clips into one, weighting each frame from each clip by the corresponding alpha value so that the RGB values stay within the same range. The resulting clip starts with one data point and seamlessly transit to the other data point. And the overlapping regions will have frames corresponding to multiple actions, in this case, 2 actions. To get the training labels, we weight the labels of each clip with the corresponding alpha value. This introduces multi-action frames similar to the downstream. Volume cut mix also introduces multi-action frames, similar to volume mix-up. However, rather than having alpha masks, here we create seamlessly varying windows within each frame looking into 2 different clips. The size of the window changes temporally so that the resulting clip will have a seamless transition from one data point to the other. And similar to volume mix-up, the overlapping regions will contain 2 actions, the labels of which are weighted by the corresponding percentage area of each window. To summarize, we introduce action boundaries through volume freeze, multi-action frames through volume mix-up and volume cut mix. If we look at how our proposed pre-training method benefits downstream detection, here we show results on charades. The graph shows mean average precision, higher the better, versus flops, lower the better. Our models, when jointly trained with the proposed augmentations, show consistent improvements at the same compute footprint. If we consider model ensembles trained separately with each augmentation, they show a further improvement, but at the cost of extra computations. Even our ensembles are 1 order of magnitude efficient compared to previous state-of-the-art. We also evaluate our model on challenging multi-thumos dataset. All models show consistent improvements similar to charades experiments. Moreover, if you look at some of our ablations, they provide key insights into detection pre-trained models. In single-stream models, each of our augmentations benefit downstream detection. And when combining augmentations, model ensembles show better gain compared to joint training. Model ensembles, of course, enjoy more compute capacity, but at the same time, the augmented inputs are not cluttered as much as in joint training. In multi-stream models, we see some interesting observations. Detection pre-trained models work very well in the trained temporal resolution, but not so much at a different temporal resolution downstream. In comparison, classification pre-trained models has a better consistency. Also, when performing a temporal aggregation, classification pre-trained models work better as they are trained in a similar setting. Considering these observations, we can combine both detection and classification pre-trained models as different streams of a multi-stream model to achieve best of both worlds. Based on our observations, The key takeaways of this work are as follows. Pre-training detection models on classification data is not ideal. Our proposed volume augmentations help design a detection pre-training task which improves downstream performance. Interestingly, there are merits to classification pre-trained models in downstream detection, especially in temporal aggregation and at different temporal resolutions. Thank you for your time, and please drop by our poster to discuss more about our work. Our code is available online. Thank you.